What's up guys, we're going to be using SQLmap to automate the process of extracting the entire contents of the database in OWASP Juice Shop. Now we can already access any piece of data from the database. We can construct a handcrafted SQL injection attack. We already have access to the entire database schema. But assuming we wanted to extract the entire database, that's going to be a fair bit of work to do that manually. This is when an automated tool like SQLmap is going to be useful. So let's fire up SQLmap. Now I can just type SQLmap because it's in my path. Alternatively, you might need to prefix this with Python SQLmap.py. If you're using Black Arch, it's automatically put in our path, so we simply need to type SQLmap. Now, straight out of the gate, we get an error because we need to provide options for SQLmap. It doesn't know at this stage what it's supposed to be doing. One of the options we can provide is -h. Let's try that. We get this help output that explains a decent amount of the most common options we'll make use of. Now, if it seems like there's a lot of options, that's just the beginning, because at the bottom of this help output, it says to see the full list of options, run with -hh. It's actually numerous additional commands that can be used. So this is the actual options that can be used with SQLmap. So that's going to be quite a bit of work to figure out what all of these options do. But what we're trying to do right now, we don't really need to use most of these options. Now we'll start with a very straightforward command. It's probably not going to give us the results we're looking for, but this really imitates the flow of how we'd be making use of SQLmap. Now let's first of all take note of our target up at the right hand side in the URL bar. So we're going to be attacking localhost port 3000, REST products search. Then we have our query string, and the parameter that's vulnerable is Q. Okay, so SQLmap. Tag U for the URL. I'm going to put this into quotes. http://localhost port 3000, and it's going to be REST products search. And now we get to our query string, and we're just going to put Q equals A, and we'll just provide a parameter. Now, SQLmap's fairly intelligent in terms of figuring out which parameters to check, but it can be good to explicitly define the parameter. In this case, we know that Q is vulnerable. Sometimes when we're running SQLmap, we won't know if it's vulnerable to SQL injection. In this case, we know that this parameter is vulnerable, and it's the parameter we're interested in targeting. So we'll put -p for parameter, and then we're going to specify that Q is the parameter we are looking to attack. Now this is a very basic SQLmap string. Sometimes it'll have good results. In this case, it's probably not going to get us the results that we're looking for, but that's fine. We can use this as a learning process. Now at this stage, it's basically telling us that it doesn't think that this Q parameter is union injectable. And it's saying because it hasn't found any kind of suggestion so far that the Q parameter is union injectable, it's asking us to skip potential other techniques. It's trying to save us time. It's telling us probably can't use a union inject attack here. So let's skip that and try something else. Do you agree with that? Now ordinarily we might say, okay, SQLmap, we accept that it's probably not union injectable. Let's skip some of those extra tests that we don't need right now. Having said that, in this case, we know that that Q parameter is union injectable. So we're not going to reduce the number of other tests in this case. We're going to choose no for this option. So the end result here is SQLmap's basically telling us that this parameter Q is not injectable. And we know it is. And this can sometimes be one of the difficult things about using SQLmap. It would be very easy at this stage to just move on and say, okay, SQLmap says there's no possible vulnerability there. But we also know that this is an extremely vulnerable web app that we're testing right now. Having said that, as you go through this process, take the time to read the output from SQLmap. It might look like it's a lot of jargon on the screen, but some of the suggestions are very helpful. So for example, in this case, it's asking us to increase values for level and risk. This will basically increase the types or volume of attacks that will take place against the web app. Now, spoiler alert, if we increase the values of risk and level, it will result in a successful SQL injection attack and it will dump all of the data in the database. However, we're not going to take that option right now. We're going to come back to that a bit later. And the reason is very simply, we don't actually need to increase the values of level and risk in order to extract data from the database. If we return to our attack string, we can see that this Q parameter starts off with a single quote, and then 2 right brackets. And the reason why we did that originally is because we were able to see the original SQL query, and we understood that this part of the query was inside 2 left brackets. So it was necessary to close that part of the query using 2 right brackets. The problem for SQLmap is SQLmap hasn't seen that SQL query and has basically no idea and would not be able to figure out that all of our union injection attacks need to start off with a single quote and 2 right brackets. It's not going to be testing for that. We can actually modify our SQLmap command to prefix those characters to the beginning of any union injection attacks. Now, to help us do this, it's worthwhile to check out the GitHub page for SQLmap. And you'll find there that there is a link to the manual. So if we scroll down, we've got some information about SQLmap. And here under usage, it references the user's manual. So if you follow that link, you'll find all of the available commands here that we can use with SQLmap and options. Now, if we just run a quick page search for prefix, we see this option, prefix equals prefix, injection payload prefix string. That's going to be useful for us in this case. So let's type prefix equals, I'm going to put this in quotes, and we know that it's a single quote and 2 right-hand brackets. Okay, so let's run that and see what we get. Once again, it's asking us if we want to reduce the number of union tests. We're going to say no to that. Injection not exploitable with null values. So that seems to refer to the union injection attack. Do you want to try the random integer value for option union character? Let's just say yes for this. Now, once again, we're not really getting what we want here, but there's another very helpful suggestion here from SQLmap. And this is why I recommend reading the output and trying to understand what SQLmap is telling us. If you do that, you're going to have a much easier ride with trying to use a SQLmap script. It says, if union-based SQL injection is not detected, which it's not, please consider forcing the backend DBMS. And it gives us an example there, tag DBMS equals MySQL. So at this stage, SQLmap doesn't actually know what type of database it's testing. And we can actually tell it what type of database it's testing so it can use more accurate injection attacks for that specific type of database. So let's just tag that on the end, DBMS equals, now it's not MySQL in this case, it's going to be SQLite. In fact, we're just going to clear the screen and run that from the top of the terminal. So we're going to say DBMS equals SQLite. All right, let's see what we get. Same as before, we don't want to reduce the number of tests. Now we're getting somewhere. Target URL appears to be union injectable with 9 columns. And we know from previous attacks that that is in fact the right number of columns for the products table. So the attack is not working with null values, but we can try random integer values for the option union characters. We're going to choose yes for that. Now it's telling us get parameter Q is vulnerable. Do you want to keep testing the others, if any? Not really. We're just trying to reproduce an attack that we already know exists on that vulnerable Q parameter. I'm not really trying to test other parameters at this stage, so we're going to choose no for that option. So it tells us SQLmap identified the following injection points with a total of 78 HTTP requests. Parameter Q is a GET request, and it's a union attack telling us there are 9 columns, and it then gives us an example of the payload. And notice that payload has the prefix which we told SQLmap about. It then goes on to tell us that fetch data is logged to text files, then it gives us a location where those text files are stored. One of the nice features of SQLmap is it keeps track of past commands run on SQLmap, and it stores results for us. And when we launch another attack against the same target, we're not starting from square one. SQLmap is able to build on those text files that have been saved. Now, although we've confirmed that the Q parameter is definitely vulnerable to injection attacks, we haven't actually dumped the database, and that's what we're going to do next. Back in the SQLmap manual, we can look for this dump all command. Dump all DBMS databases, tables, entries. So it's basically going to rip all of the content of the database and all of the tables and the values in each of the columns. So let's tag that on the end, dump all. Basically the same query, we're just asking it that we want to extract the data from the database now. Let's run that. Now we run into an interesting issue. It's saying unable to retrieve the table names for any database. Do you want to use common table existence check? So it's asking us, would you like to test for common table names to see if they match any of the tables in the database? That's not really what we want to do in this case. We know that it's fairly trivial to extract the table names from the database. The question we're trying to understand the answer to is, why wasn't SQLmap able to see that? We can see that information very easily with manual SQL injection attacks, but apparently SQLmap doesn't really have any idea what's going on. Notice we get this warning. First it says the SQL query provider does not return any output, so that's strange. Then says in case of continuous data retrieval problems, well that appears to be what we're having, you are advised to try a switch Nocast or switch hex. Now it does explain to us on the manual what that is. It says when retrieving results, SQLmap uses a mechanism where all entries are being casted to string type and replaced with a white space character in case of null values. Now that's really not that surprising or interesting, but the important part here, it says, nevertheless there are reported cases where this mechanism needed to be turned off because of problems with data retrieval itself. None values are being returned back. Well, that appears to be what we had. It said the SQL query provider does not return any output. So let's rerun that query. We're just going to exit out of here. Let's clear the screen. And we're going to add the Nocast option. Now we're almost there with this. But there's still something further we can do to improve this particular SQLmap command. Notice here it's actually starting to pull information from the database. There are a whole number of tables there that it's retrieved the name of the table. It then turned its attention to the captures table, and it starts trying to fetch entries for the captures table after it's already fetched the columns. Then all of a sudden, everything seems to be going fairly well, and it says, unable to retrieve the entries for table captures in database SQLite master database. Then it tries to fetch the columns for table privacy requests. Once again, same problem, unable to retrieve column names for table privacy requests. Then it's asking us once again if we want to essentially use a dictionary to try and find the names of the columns in this table. We don't really want to do that because we know it's very straightforward to extract those. Now what we notice is it keeps going. Some things are succeeding, some things are failing. Now there would have been a helpful error message at some point of this, and I think we may have missed it. And one of the ways that we can reproduce that is to just start the process again. So we're going to do that right now. We're going to open a new tab. And we're going to head to this location where everything is stored. And we'll run the command remove r localhost / just to get rid of any saved data that SQLmap has on this target. Now I'm going to run that command again. And let's pay attention to any error messages along the way. Now notice this warning. Parameter length constraining mechanism detected. Potential problems in enumeration phase can be expected. Now, what's happening in this case is that there's a length constraining mechanism detected on that Q parameter. And you'll see if you were to use something like a proxy like burp or zap proxy, you would see that some of these injection attacks involve very long parameters. And part of the reason for the very long parameters is that some of the values as part of that SQL injection payload are being escaped. We can see an example of this if we have a look at Noescape, and it just so happens it's the very next command after Nocast. So it says in cases when SQLmap needs to use single quote delimited string values inside payloads, those values are automatically being escaped. You can see an example of that. So if you compare select foobar to car102 plus car111 plus car111, you can see that after being escaped like this, it's a much longer payload. Now there are legitimate reasons why this is done. For example, the obfuscation of the payload, but this is causing a side effect where we have a much bigger payload than we would ordinarily have. So we can use this toggle Noescape. That's going to turn off the escaping of the payload, and it's going to reduce the payload size, and it's going to help us bypass this length constraining mechanism. Okay, so let's clear the screen. Let's rerun that. Same command as before, we're just going to add Noescape. Let's see if we're going to finally get some results from our SQLmap command. Now we're clearly getting some results. It's doing a much better job of enumerating the data in the tables. However, we are still getting intermittent warnings. So for example, it says possible server trimmed output detected, probably due to its length and/or content. So not only was GShot refusing to take payloads above a certain length, but it seems that it's also trimming output above a certain length. So depending on the length of the output or the type of data it could be in some cases, we're not actually able to get all of the data from the database. So you have a decent amount of it, but we haven't actually enumerated everything right now. Now that's fine, let's backtrack slightly. And let's pretend we're going to start this problem again from the beginning. We're going to delete that folder where we have the SQLmap data, and we're going to construct a new SQLmap command. And we'll just build off the old command, but we're going to go back to the original command where we just have SQLmap, we have our URL, and we're saying that we're interested in analyzing that parameter Q. Let's run this. And let's just pretend that we don't know that this app is union injectable, and we're just looking for any kind of successful SQL attack that we can run here. So we'll say that we don't want to reduce the number of requests, and we're once again back to the beginning at a point where SQLmap's telling us it doesn't really think that the parameter Q is injectable. However, it says we can increase the values for level and risk. So this is what we would typically do. We didn't follow this path before because we already knew that this app was union injectable. But let's just pretend we didn't know that. Now level can actually be run anywhere between 1 and 5. We're going to set level to 3 and we're going to set risk to 3. And let's run this. Now, given that it's allowed to run extra tests, it's now telling us that parameter Q appears to be injectable. But it's not talking about union injection. It's actually talking about a type of blind SQL attack, Boolean based. Also, with the extra tests, it's figured out itself this time that the database system is SQLite. It says, it looks like the backend is SQLite. Do you want to skip test payload specific for other DBMSs? Well, there's no reason why we'd be running MySQL specific payloads, for example, when it's an SQLite database. So it's completely okay and standard to skip these tests for the other database systems. For the remaining tests, you want to include all tests for SQLite, extending provided level 3 value. Well, we're completely okay with running everything in this case, so we'll just choose yes. Now the process did actually complete in this case, we have confirmation that the Q parameter is injectable, but it's talking about Boolean-based blind. Now, although we might be able to extract the contents of the database using a blind SQL injection attack, it essentially involves asking the database a long series of true and false questions for every single character in the entire database structure. In other words, it's absolutely not the most efficient way to enumerate the database. Having said that, it does seem that we weren't able to completely enumerate everything in the database using the union injection attack, and that's because some of the output appeared to have been trimmed by the server. So given that, let's see if we can actually enumerate the entire database using this blind SQL injection attack. Now, don't worry too much if you're not familiar with blind SQL injection. We're going to run some manual blind SQL injection in some of the later videos. But for now, let's see if we can get SQLmap to use this blind SQL injection technique and dump the database. Now, just so you know, in the case of the time-based attack causing problems with the server, it's actually possible to specify that we only use some of the techniques that SQLmap has available. And we can control this with the technique tag. So notice we had a small issue during the process. We actually have a warning and a critical error there. So it does seem that the Node.js server wasn't responding for a period of time, but it did actually manage to bring itself back online. So we had a critical error, then the warning, most likely web server instance hasn't recovered yet from previous time-based payload. If the problem persists, please wait for a few minutes and rerun without flag T in option -- technique. Now in this case, we don't need all four of those options. So that B, E, U, and S each stand for a type of attack. So we've got B for Boolean blind, which is what we're interested in. E for error-based. U for union query-based, so that's what we were exploiting previously. And S for stacked queries. Now T stands for time-based blind, but because that's potentially causing problems for the server, we can remove that, which is why it's saying rerun this, but exclude the option T from the technique flag, because potentially that could be taking your server offline. I'm surprised the process actually completed this time. However, we already know how the database is vulnerable. It's vulnerable to this Boolean blind. So we can actually just specify that it only uses that type of attack against the server. So we'll put technique equals B, and we're now going to append dump data. Now these Boolean-based SQL injection attacks can take a long time to enumerate the entire database. But that's fine, we're just going to leave it running and speed up the process. We'll just fix our syntax there. So instead of dump data, we actually want dump all. Now notice how it's enumerating things very slowly, character by character. If you saw this and didn't understand what was going on, you might assume that the process is lagging quite heavily. But the truth is, for each of those characters, a number of SQL injection attacks are taking place. We'll cover this in more detail a bit later, but essentially we're asking the database, is the next letter A true or false? If it's false, then we ask, is the next letter B true or false? If it's false, we ask, is the next letter C? And we essentially keep asking those questions for every character in the entire database. It takes a long time, but with the entire process, we're able to dump the contents of the entire database. And the good news here is, since we're just operating based on true and false responses from the server, we don't need to worry about any of the output being trimmed. Alright, so the process is complete. It took a super long time, which is why I actually stopped recording at some point during the process. It has managed to successfully dump all of the contents of the entire database, and it even gives you the option to attempt to crack some of the password hashes that it extracts in the process, and it was actually able to convert some of those password hashes into their plain text values. Now at the end it gives us this message that it's dumped to CSV file, so let's go and check out that newly created file. In fact, we can see that each table in the database has been given its own .csv file. Let's just attempt to cat these to the screen. So we can see the content of the database. We can also just use the column program. So we'll do column -s -t, and then we're just going to pass in one of those CSV files. It's perhaps slightly more readable. If you have some kind of Office package installed, for example, LibreOffice, I'm fairly sure that you could just open these .csv files in a spreadsheet format if you prefer that. The key concept here is that all of the tables have been dumped here. We would presumably most be interested in something like the users table, so let's just check that out. Now, if we look at the password column there, we can see the hashes for each of the user accounts, and notice that some of the hashes have a bracket and then a plain text password in them. And this is what the MD5 hash cracker was able to pick up. I guess it's just using a MD5 dictionary for this, but it's found out some common passwords and was able to determine them from the hash. So we've got admin123 and we've got demo as a password here. The rest of the hashes were not crackable with this specific attack, but they could well be with a more sophisticated attempt to find out the plain text passwords that these hashes represent. Now, just thinking back to the beginning of this session, we deliberately avoided this blind SQL injection attack because it wasn't going to be the most efficient in terms of time way of getting the data from the database. And it has taken a long amount of time, which doesn't really make sense if we have a union injection attack, because that could just read all the table information in plain text when it's returned as part of that JSON response. But as we saw, some of those JSON responses were evidently being truncated, and we weren't actually able to extract all of the data from all of the tables using that technique. But a lot of the time, if something is union injectable, you will be able to extract all of the data. So it wouldn't make sense to invest quite a number of hours performing a blind SQL injection attack to enumerate the entire database when we have another option, the union injection attack, which is going to be a lot faster since it's not blind, it's not Boolean based. So however we go about this, we've reached our end goal, which was to dump all of the data from the Juice Shop database, and we've used SQLmap to help us do this. Thanks very much for watching, guys. Time to fire up SQLmap and have some fun.